We're asked to solve sine x equals negative square root 3 divided by 2 for all solutions, give exact radian answers, use k to represent any integer. We will solve this equation using reference triangles and then verify these solutions using the unit circle. The first thing to notice here is that the sine function value is negative, and since sine theta is equal to y divided by r on the coordinate plane, sine is negative where y is negative, and therefore we're looking for angles in the third and fourth quadrants where y is negative. The next step is to find the reference angles in the third and fourth quadrants that give a sine function value of negative square root 3 divided by 2. To do this, we ignore the negative sign for a moment and find the reference angle that gives a sine function value of square root 3 divided by 2. If we sketch these reference angles in the third and fourth quadrants, the sine function value will be negative. So having a sine function value of square root 3 divided by 2 should remind us of the 30, 60, 90 reference triangle shown here. And since sine theta is equal to the ratio of the opposite side to the hypotenuse, notice sine pi over 3 radians is equal to square root 3 divided by 2. Which means we need to sketch a reference angle of pi over 3 radians in the third quadrant as well as in the fourth quadrant. And let's also sketch the reference triangles. For the reference angle in the third quadrant, the opposite side is negative square root 3, the adjacent side is negative 1, the hypotenuse is 2. For the reference triangle in the fourth quadrant, the opposite side is negative square root 3, the adjacent side is 1, and the hypotenuse is 2. Notice using both reference triangles, the sine function value is negative square root 3 divided by 2. But remember, we're looking for all the solutions, so we're looking for all the angles that are coterminal to these two angles. To begin, let's find the least positive angle in the third quadrant, which would be this angle here. This angle is equal to pi radians plus pi over 3 radians. Adding, we have 3/3 pi radians plus 1/3 pi radians, which gives us 4/3 pi radians. So let's start with x equals 4/3 pi radians, but then again, any angle coterminal to this angle would also give a sine function value of negative square root 3 divided by 2. To find all the coterminal angles, we add multiples of 2 pi radians, and therefore we add 2 pi k, where again k represents any integer. And now let's find the least positive angle in the fourth quadrant, which would be this angle here. Notice this angle is equal to 2 pi radians minus pi over 3 radians. So 2 pi minus pi over 3, common denominator is 3. We have 6/3 pi radians minus 1/3 pi radians, which gives us 5/3 pi radians. So we also have solutions in the form of x equals 5/3 pi radians. And then again, to get all the coterminal angles to the angle in the fourth quadrant, we add multiples of 2 pi, giving us plus 2 pi k radians. And now we have all of the solutions to the given equation. And now let's verify this using the unit circle. Remember, on the unit circle, sine theta is equal to y. And again, we know y is negative in the third and fourth quadrants. So to solve sine x equals negative square root 3 divided by 2 using the unit circle, we begin by looking for a y coordinate equal to negative square root 3 divided by 2, which we have here at 4/3 pi radians and here at 5/3 pi radians, which of course gives us the same solutions, which means all the solutions, once again, are in the form of x equals 4/3 pi radians plus 2 pi k, as well as 5/3 pi radians plus 2 pi k. And then finally, let's verify some solutions graphically. Here we have the graph of y equals sine x in red and y equals negative square root 3 divided by 2 graphed in blue. The first thing to notice is that the horizontal line will intersect the sine function in an infinite number of points, which is why we have an infinite number of solutions. Next, the first angle we found in the third quadrant was 4/3 pi radians, represented by this point here. And if we add 2 pi radians to 4/3 pi radians, we would get 10/3 pi radians. If we add another 2 pi radians, we would get 16/3 pi radians. The angle we found in the fourth quadrant was 5/3 pi radians, represented by this point here. If we add 2 pi radians, we get 11/3 pi radians. And if we add 2 pi again, we get 17/3 pi radians. And of course, we could also subtract multiples of 2 pi radians to move in the negative direction. So this graph does verify the expressions we found for the solutions are correct. I hope you found this helpful.